So beta can be positive beta and negative beta. When is it a positive beta? So let's say there is a nucleus and it has more neutrons than protons. So then it wants to get rid of a neutron, and then it will say, okay, let me produce one proton and one electron. So it will have a beta decay. But then there may be another nucleus which has more number of protons. It wants to get rid of a proton. So then it says, okay, let me make this a neutron and a positron. And this is going to be a beta positive. Okay. So just go through these slides one more time. Any doubts, please let me know. I've already covered this yesterday. I'm covering it again today. Unless it is 100% clear, you don't say it is clear. Anybody has any questions on this slide, please tell me. Okay, so the next slide here is this. So the reactant was the original thing here, right? The product is whatever product you have. So the difference in mass is the release in energy. So products are this and this, right? And this and this. So when you add up all those masses, it's less than that. So the delta of the mass is converted into energy. E equals mc squared. The most famous equation there. Beta positive. So this will happen when there are a lot of protons. So the neutrons are less and protons are more. Right, so you'll have beta positive. So any questions, any doubts? Okay. So next slide here. So I think we already covered this. So let's talk about nuclear stability. Yeah. So now this is the line, the solid line. Look at this. This graph is really helpful. I mean, most of the graphs, there are a couple of graphs only. The solid line that you see here represents the stable nucleus. Okay. For stable nucleus, n by z is equal to 1. Right. For over here. So I'm going to draw myself. So let's say this is a graph. So when you start drawing that, you will actually see a line with a slope of 1. But overall, later on, it is going to slope like this. So what happens in this zone, the stability requires that n by z, which is the number of protons by the number of neutrons by protons, it is equal to 1. But when you come to the heavier side, stability demands that n by z is close to 1.6. And that is why you don't have a straight line, you have a curved line draw. So this line shows the stable nucleus. So when you have elements in this area, that means you have more neutrons out there, right? So as we already saw, if there are more neutrons out there, then it is going to be a beta negative decay because one of the neutron will convert into proton and electron, right? But if you have something in this region, what is going to happen is beta positive because you have more protons. Proton will convert into neutron and a positron. Okay, so anything on this side is going to give you beta decay. The other side is beta positive. Anybody who did not understand, because I'm not sure, nobody is asking any questions. There have to be some questions out there. Okay, gamma decay. So gamma decay, as we already said, gamma is pure energy. It's just a photon. Photon is purely energy. There is nothing like, there's not even concept of rest. So there is no concept of rest mass anyways, right? So when the nucleus undergoes a radioactive decay, so as we saw, it releases alpha particle, beta particle, but again it is not satisfied. It goes from a unstable state to a less unstable state. It's still not stable. In order to achieve that stable state, it is usually going to decay some kind of photon out there. That is the secondary decay. Anybody who does not understand what I'm trying to say. So there is a nucleus here, it releases alpha particle, it becomes less unstable. Now it still has to go through stability, so it releases a photon, and that is going to be a stable state. Manjushri, has this been clear to you? Sai Kumar, Nina, Abhinaya, Grishma, Shivangi, is this clear to you? This slide. ठीक है. If it is clear, then well and good. ठीक है, no issues. Yeah. So look at an example here, right? So boron, right? So you start with 12 boron 5, and you get an beta decay. So when beta decay happens, this is going to increase by 1. Remember, neutron is converting to proton, so proton number increases. But the mass number does not increase because number of neutron has reduced, proton has increased. So 12 remains 12. It becomes carbon 12 now. Right? But you can see the asterisk there. This is an excited state carbon. It is going to release a gamma radiation to become a stable carbon. So this is a two-step process. First of all, a beta decay and then a gamma decay. I'm assuming everything is clear. So no questions, good news. That's all I'm assuming. Right? Fundamental laws of radioactivity. These laws will always be valid. Now, this is where we are talking more about mathematics part, where we say activity, half-life, how many are disintegrating. So if you talk about this here, you had boron, but boron converts into carbon. So it is no more. So let's say you had B, 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 B. My name starts with B, so I'm happy there. So, right. So after some time, in the container there was 16, so this is converted into carbon. You don't have any more of that. Maybe this is converted into carbon, right? First of all, radioactivity is a spontaneous process. Spontaneous process. What that means is I know in every second how many will decay. I know in 1 minute how many will decay, but I don't know who is going to be next. So I don't know who is next. It's completely a random process. Maybe this is gone. Maybe this is gone. Right. So I started with 8 of these and I'm left with 4 only. So whatever time it took for reducing to half is called the half-life period. So let's take an example. It took me 1 day. Right. So let's say some element has a half-life of 1 day. So I start with maybe 256 nuclei. Okay, after 1 day, tomorrow at the same time, if I come, I have to expect 128. And after some time, I come back, like after 1 day exactly, I come back, I will see 64. After one more day, it is going to be 32. So you can see what is happening. After one half life, the amount of nuclei remaining there is reducing to half. Okay. But that also means the activity is reducing. Activity is every second how many are disintegrating. There was a lot of activity here. There is a reduced activity here because only in 1 day only 64 has been disintegrated now. Now this is lesser activity. This is lesser activity. So I can say activity actually depends on the number that I have in the container. More the number of nuclei there, more the activity. Okay, activity, right? Activity is also like number of nuclei disintegrating per unit time is proportional to n, or you can say negative n because it is reducing now. Okay, I'm not sure, nobody is asking questions for past couple of classes. So is it really clear to everybody here? Atri, Ganit, Abhinaya, Ashik, Manjushri, Nina, Rhythm, Rupa, Rukaya, Sai Kumar, Shivangi, Shreya, Hegde, and Trisha. Is this really 100% clear? Okay, ठीक maybe I've studied this in chemistry also, so that is why. Okay, so let's go through some of this. So we are saying activity is directly proportional to the number in the container you have. If you have a 1 million nuclei, there is some number disintegrating, but if you put in 2 million there, the activity becomes double, exactly double, right? So activity is proportional to n. In order to remove that proportionality, you plug in a constant there. And this is called the decay constant. This is called the decay constant. So how many are disintegrating every second? How many nuclei are disintegrating every second there? ठीक है भाई, चलो. Right? So I'm going to do all these derivations for you anyways. So let's talk about this. Now dn by dt, which is the number of nuclei disintegrating every second, is equal to negative of lambda n. Whatever is in the bucket there, it's proportional to that. Negative sign means it's reducing. The rate of change is reducing, right? It's a negative change. So let's rearrange all this. This becomes dn by n is equal to minus lambda dt. You can integrate that. Limits would be you start with n naught as in the original number, and how many do you have now? And you integrate here. Lambda is constant, so it can stay outside of all that. So integration of dt from time t is equal to 0. I start my stopwatch now, and I stop it after t seconds. So I'm interested in how after t seconds. So after t seconds, how many nuclei are left in there, right? That's what I'm interested. Anybody knows the integration of 1 by n, dn by n? Anybody who can tell me what is the integration of the left hand side? Awesome job, Sai Kumar. Yes. Anybody else? Yes, Ganit. Yes, you're right. Ganit is right. Rukaya is right. Abhinaya is right. No need not do it one more time. Um, yes, Manjushri, you're right. Good job. Yeah. So some students have written log. You should actually prefer to write natural log like this. Okay? That's the only thing I would recommend, because it's natural log, it's not the common log. So there are two types of logs, one to the base 10, which is called common log, one to the base e, which is natural log. So this is natural log, right? Other than that, everything looks good. So this is natural log of n, है ना? So then limits are n naught to n is equal to minus lambda. What is the integral of the right hand side? Integral of dt, please. ठीक है Ninad, good. Ganit good, Sai Kumar good. Okay, good job there. Awesome guys. Yes, Atri is more accurate. Everybody is right. Atri is 100% right. Okay, everybody is 99% right. Right. So Atri is saying this. So everybody, please listen here. What is the integration of this? What is integral of this? Please tell me. What is integral of x to the power n? Or let's say x to the power. Let's actually take x square. Maybe x square. What is integral of x square? Anybody, please. Yes, Ninad, you're right. Yes, yes. Rukaya is 100% right. Ganit is 99% right. Atri Patel is 100% right. Sai Kumar is 100% right now, right? So the 100% right would be x cubed by 3 plus a constant. Right? What is integration? Integration is ulta, the opposite of differentiation. If I differentiate this with respect to x, I'm supposed to get x square, and I do get x square, 3x square by 3, but in differential of this is 0. So you're always supposed to write plus c there, right? That is good. But then when you have to put limits, that c crosses out, so you don't care about it. Yeah, Vasudeva, what happened? You have not been joining classes for a long time now. Okay, t from 0 to t, right? So that's fine. C will cross out anyway, so that's why I've not put this. Now, if you look at the left-hand side, for the students who don't understand logarithm properly, I'm doing this a little slow here. So this becomes minus lambda t minus 0. Now log a minus log b is log a by b. Yeah, Vasudeva, what happened? I was actually worried. You didn't attend past couple classes, I guess. ठीक है, ये हो गया. Now you can rearrange this. This becomes n naught by n is equal to e to the power minus lambda t, and that gives you. Did I do ulta? I did ulta here, maybe. Something doesn't add up here. Mm, something is not right here. Hannah, something is not right, because I'm supposed to get negative there. Something is not right there. Vasudeva, I'm not sure what you're saying. No, Vasudeva, this is actually we are doing. Okay, I found the mistake. Thank you, Sai Kumar. I was thinking two things. So Vasudeva, we are doing radioactivity as of now. Sorry, everybody, I messed up there. Okay, yeah. So n is equal to n naught e to the power minus lambda t, right? So what we learn here is, let's say you started with a bucket having n naught number of nuclei. After t seconds, you will have these many nuclei remaining in the bucket. where lambda is actually the constant, the decay constant that we were talking about. Now, if this is 100% clear, I'll proceed here. Is that clear? Everybody say yes or no. Okay, please proceed. Okay. 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 So now let's proceed to what is half-life then. Vasudeva, you have to see a few recordings or study yourself. You were actually missed in the class. Please join all the classes. Okay. So this is what we started with. Yes. Sai Kumar is asking, is decay constant different for different materials? Yes, it is different for different materials. Half-life can vary from 10 to the power maybe -8 seconds to a few thousand years also. It's a wide range. Carbon 14 is something like 5740 years or something, right? And I'll talk about carbon dating after that. So let me write carbon dating. We'll talk about it. Okay, without a now this is what I have. Okay, so now we said, okay, what is half-life? Half-life is whatever I have here. Let's say we have 1000 nuclear here. How long does it take to convert it to 500 nuclei? And the same amount of time will be taken to bring it down to 250. So how much is the half-life now? That's what you're trying to understand. So at half-life, when time is half-life, the number of nuclei should be half of what you started with, minus lambda t half-life, right? We are saying half-life. When t half-life has passed, the number is this. So for students who don't understand logarithms much, I'm doing it slow for you. Okay. So now you can do this ulta because this is negative, this can become 2. So 2 is equal to e to the power lambda t half. This can also be written as lambda t half is equal to log of 2, natural log of 2. But the natural log of 2 is 0.693. So half-life period is actually 0.693 divided by lambda. So this is how these are related. If I know the decay constant, it's related to half-life like this. 0.693 divided by lambda. That's another expression you're supposed to always remember. Or you can derive it like 3, 4 lines. It's up to you. You mean by half-life? Yeah. Ninad has asked a question here. So Ninad, this is the point. Uh, let's say let's say lambda is something like I don't know 0.0693. Let's say some number I have taken there. Okay, so then t half life comes out to be 0.693 divided by 0.00693, which is 100 seconds. So what happens after 100 seconds is this. So let's say I started with 256 nuclei in the container. I have a container here. I put in 256 number of nucleus or nuclei. After 100 seconds, when you watch here, 128 are gone. Means 128 have converted to something else, right? Like boron was converting into carbon, so it's converted. You only have 128 remaining. Now after 100 more seconds, it's half of what is left now. It's not going to be 128 gone. Half of them are gone of whatever is remaining. So 64 remaining. Then after 100 seconds, oh, you still have 32 now, right? So it goes on reducing a half. Right? So now that's what I was saying. The activity is also reducing. Every second, less and less number are decaying now. Any questions? Vasudev, are you understanding? Ninad, is this clear? Yes. So the laws of nature are laws of nature. We decided to call them physics or chemistry, doesn't matter. Right? So Vasudeva, whatever you study in chemistry is going to be same here, except conventions can be different. Like in the first law of thermodynamics, there is a big difference in how you write the law in chemistry and how you write it in physics. But behind the scenes, there has to be same fundamental things. Yeah, the mass decreases because you are reducing you're giving away energy, right? The mass is going to reduce because we already saw boron converting into carbon, it releases some energy anyways, right? By that beta decay and gamma decay. So the mass of this is less than this. It will be given. So Sai Kumar, gamma decay is something that you find experimentally. You should be given that. And if you're not given, you'll be given half-life and you have to calculate gamma, right? Not gamma, sorry, the lambda, right? So lambda is a constant that is experimentally found. ठीक है? Any questions, please ask. Okay, so then we were talking of carbon dating. And as I said, I'm really poor in memorizing things, and biology, civics, chemistry, not chemistry, chemistry was good. So biology, history, those were really challenging subjects for me, right? So I'm not going to tell you the exact numbers, which I really find difficult to understand. So carbon 12, carbon 13, and carbon 14. Carbon 14 and 12 are the most abundant, right? These are isotopes. We spoke about isotopes yesterday. Okay, let's actually see how much is it there. One second. Let me Google, and I will actually Google because I don't know it's 99% or what. So percentage of carbon 14 um, in nature. Okay, I'm Googling for percentage of carbon 14 in nature. So that's carbon 14 is very less. Carbon in a trace amounts, right? So very less. I mean, it's really tiny. So let's talk about that. So we will cover the whole thing here. So there is carbon 12, carbon 13, and carbon 14. Okay. So now we are more interested in carbon 14. So nature में क्या है? This is roughly like 99%. This is roughly like 1%, but not exactly 1%, tiny less than 1% because you have traces of this also. So just for understanding, let's do this. We will say, okay, this is 0.9% and this is 0.1%. There's no harm. We are just trying to understand. We are taking some numbers here. Okay, so please listen here. Yes. Ninad, please listen here what I'm explaining. What you're saying is exactly what we are covering here. Okay, so once I'm done explaining in 2-3 minutes, you can ask questions. So this is how the composition is in the nature. So most of the carbon is in the stable form here and here, but there are tiny traces of this unstable kind of. This is the one which shows the decay. Shreya, but what happened? You're very late today. So please see the recording of whatever you missed. Okay, please do see that. Now carbon exists as this thing, right? So every human being, every animal, plants, they consume carbon in one form or the other. We eat food. Some of us might be non-vegetarian, so we eat meat. I'm purely vegetarian, no eggs, nothing. But we eat animals, we eat plants. So whatever we eat, we are actually consuming carbon. Okay. So when we consume carbon, we are actually consuming the carbon in the same percentage. This, this. So when you take the carbon percentage here, you will actually see exactly what happens in nature. Exactly the same amount. Now let's say there is a dinosaur, and don't laugh when I try to make something. Maybe I'll make a tree. I'm not artistic. So tree. So tree has this amount of carbon, or maybe a dinosaur, right? Dinosaur has exactly this amount of carbon when the dinosaur was alive. Now the dinosaur is dead, let's say. So dinosaur is not eating anything now. It's whatever was in the body is in the body, right? It's not eating. Now what happens now is this is radioactive. This thing is radioactive with a very large half-life. If you can recall, it is something like this, these many years. Okay. So now what will happen is whatever was the trace of the carbon 14 there, it is going to reduce to half after 5740 years. Okay, so Ninad is saying let this tree be the leg of the dinosaur, right? That's the bone maybe. Okay, okay. So now after 5740 years, it's going to be half of what it was earlier. After 5740 more years, it is going to reduce further half, further half, further half. Then let's say I find a piece of dinosaur remains and I do the lab analysis and I find this percentage is reduced down to let's say 0.1%. Okay. So now what I understand here is I can always use this expression e to the power minus lambda t. So I know how much is in percentage wise, right? Is now how much percentage was it when it was alive, and then lambda, I already know this lambda is coming from this, right? So then I can know the time period. I know how much time has elapsed since this dinosaur was dead, and this is called carbon dating. You can find the age of the dinosaur or age of anything that is fossil, that was living sometime and now it is not living, by using radioactivity. ठीक है, can I move on now? A brief introduction हो गया. Anybody who did not understand? Got it. Aturi got it. Okay. Shreya Bhatt, did you get it? You joined late. Did you understand this? Or have you already studied this maybe? Okay, Sai Kumar got it. ठीक है, ठीक है. As long as you got it. So let's see. So we already found how much is remained. So how much is decayed? Obviously, how much is decayed is how much you started with minus how much is remaining, right? That's what we are doing. This is nothing new, but the same thing. You're subtracting. So half lives, we already did it. So I'm going to just show you the slide here, not going to speak anything. This is how these are related. 0.693, you have to remember that that's log 2. Okay. If no doubts, then I'm going to move on. So number of nuclei present after n half-lives. Let's see what this is talking about. Let's say you had n naught. Take it now. Now, as in now, your container has n naught number of nuclei. After one half-life, you will have n naught by 2. है ना? And after two half-lives, you're going to have n naught by 4, which is actually 2 squared. After three half-lives, you'll have n naught by 2 to the power 3. Taking it further, after n half-lives, you will have n naught by 2 to the power n. So this is the number of nuclei you will have after n half-lives. ठीक है, आधा हो गया, 1/4, 1/8, 1/16, 1/32, 1/64, and so forth. As the time is passing, the number of decays are also reducing. The activity is reducing. ठीक है? So Shreya Bhatt seems to have understood that. Okay, so this is the same thing I spoke about. Okay. Please, everybody work on this. I'm expecting everybody to give me the right answers here. I'm going to write some options maybe. So let's call this A because I can give a poll on this then. Yeah, everybody give me the right answer here, please. Atri, yeah, obviously that answer is right, Atri. Sai Kumar, you're right. Nina, do it carefully. Nina, read the question carefully. I'm 100% sure you can do it. Yeah, Ganit, yeah, you're right, Ganit. I'll pose the poll in maybe 30 seconds now. Vasudeva, that is right, okay. And for the students who were absent for past few days, yesterday we started doing a bonus kind of thingy. We did from 11 o'clock for 15-20 minutes, we did introduction to special theory of relativity. So today we are going to do the same thing, extension of that. For 15-20 minutes. It's an optional thing. It is not part of the curriculum. If you think you're going to get confused, don't join that. This is really a disclaimer. Sometimes students start getting nightmares and dreams of special theory of relativity. So do not join it if you think you're going to have that situation. It's really confusing thing. So you're welcome to join, but don't join if you think you will be confused. Your curriculum takes a high precedence over those things, please. Okay. So here is the poll. A, B, C, or D, please. 100% right results, please. Okay, so far 100%. Okay, 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 still good. 19% students have voted. Everything is good so far. Now wrong answers are coming in. क्योंकि question नहीं पढ़ा. I'm telling you, didn't read the question. You're doing the right thing. You're on the right track. You're not reading the question. I request to read the question carefully. ठीक है, so I'm going to close the poll now. I was actually hoping 100% right here. So answer is C. Okay. So two half-lives, right? Two half-lives में क्या होगा? Like this is so easy. I mean, there's nothing much to explain here. Now you have 6 times 10 to the power 18. After one half-life, you'll have adha of this, right? Half means half. That's it. After two half-lives, you're going to get half of this. ठीक है? Clear? All clear? ठीक है. Let's move on then. ये है मतलब this is the solution maybe. Okay, activity we already spoke about. So activity is dn by dt, so activity also is going to be a naught, right? So if you want, I can do that on a blank slide. That will be better. So dn by dt है ना, is equal to negative of what you have. Yeah, what you have is this. ठीक है? Oh, sorry, my bad. Of what you have, right? Now this thing is called the activity, what's happening right now. So then activity is equal to negative of lambda. N can be written as n naught e to the power minus lambda t. ठीक है? At time t is equal to 0, activity 0 is minus lambda n naught. Because when you plug in 0 here, anything to the power 0 is 1. है ना? E to the power 0 is 1. So that's why we're getting it. So minus lambda n naught can be written as a naught, as in the initial activity. So as the time passes, compared to initial activity, this is how this is related. So as time increases, activity reduces. At time t equals to 0, activity is activity naught. At time t is equal to infinite, activity becomes 0. So it is going to be an exponential kind of thingy. It's an exponential graph, exponential decay. This is an asymptote. So this graph is never going to meet x-axis. It's going to meet the x-axis at infinity. Can I move on? Is this all clear to everybody? You got to say yes or no. I'm not going to move on. Some students have to say yes, no. ठीक है. Thank you for that, right? So all this derivation I'm not doing. So average life क्या है? कि look at this. You had this container. यहाँ पे there was some nuclei there, right? So it's not a cheese. It's the container with nuclei there. So what happened is this decay, right? It's gone within, let's say, 1 second. Next second, this is gone. Next second, this is gone. So this lived for 1 second, this lived for 2 seconds, this lived for 3 seconds, and so forth. So how much is the average of the life of a nucleus there? That will be the total time they have spent alive divided by the number of nucleus, more like an average there. So the average life is given as 1 by lambda. So this is the average life a nucleus is living there. Okay, remember this also. You got to memorize a few things there.